All right, we should be live. Welcome everybody. Steve George and Danny Davis with Kennametal.
How's it going?
Yeah, glad to see everybody again, and we hope you enjoy today's webinar. So just kind of a quick greeting. So again, I'm Steve George. I'm lucky guy that gets to be I'm the senior manager for R&D and engineering for the Solid Rounds group. Really enjoy what I do, have a great team. My good buddy and friend Danny here, we've worked together for a long time. Together we've got over 60 years of experience in this industry.
Yeah, it really makes me feel old.
And well, I think that goes both ways, but we're really happy to be here together, and really glad to have Danny as my partner. We hope that everybody's safe during these times. Certainly it's very difficult for everybody, and we hope that you are all safe. We're certainly practicing good safety practices ourselves, and usual social distancing. In this case, we're a little closer together, but you may or may not see it, but we have a Lexan shield going across, kind of partitioning us off here a little bit. So still able to talk together and talk to you guys, hopefully have that experience for you today, but we are practicing safety between us. So with that, let's get into what we want to talk about. And today we want to talk about our new HARVI I TE product, right, Danny?
Right. Yeah, we want to talk a little bit about the versatility of the cutter. I think that's the main thing that we want to talk about today. I think that's something that's really not mentioned that much when we talk about it. We always talk about how sophisticated the tool is, how much engineering went into it, how great a tool it is, but it's also a very versatile tool. And
absolutely,
I know we talked about before, Steve, but if I had just one tool to pick out for my machine shop, if I had a small machine shop, it would be this tool.
Absolutely, yeah.
There's so much versatility, and I know we have a video that we can show, just showing some of the versatility as far as the cuts go, and then we'll talk a little bit about the materials as well. But the video we've got, and this kind of break the ice a little bit, I think, too, in the webinar. So maybe wet your whistle a little bit and show you some of the capabilities. But let me pull up that video, Steve.
Yeah. So, and while Danny's pulling it up, we kind of show on the screen here. We've been, really great that we were chosen to receive the 2020 Edison Award, basically an innovation award for the HARVI I TE. Really proud of our team and everybody that's worked together to deliver that tool. That's really a great award, and we're very honored to receive it. Really took a lot of hard work in developing this tool, and again, that's part of why we're so excited to talk to you about it today. So
I think the Edison Award really speaks about how sophisticated and how much engineering actually went in this cut.
Absolutely. So
here we go. We'll go ahead and start the video, and through the video, we've actually silenced it so we can talk through it a little bit, but we want to talk a little bit about some of the cuts that we have in this video. And you can see this video also on our Kennametal
YouTube please channel. Check out our Kennametal YouTube. You can please give it a like. If you want to, you can subscribe. You can even get notified when we drop new videos. But what's really nice about this video is it demonstrates really just how versatile it is. So we went from a finishing cut there to a fine finishing cut. Definitely we're going to jump in here to roughing cuts and different ways to enter the material where this tool really shines. So here we're going in already to a heavy roughing operation. You see both deep in terms of axial and radial engagement. Chips just flying out of there in a good block of basically 4140. Now we're going in with a 1.5 times D slot. Going to kick that up here in just a minute to an even deeper slot. See those chips just flying out, and we'll talk about why that is, and what we've done differently on the tool to be able to achieve that. I just love seeing this cut.
Yeah, it's
2 times D cut, blue chips flying out, and just going everywhere.
So this is a 2 times D slot.
This is a 2 times D slot, which obviously is just extremely impressive, and I think that's one of the things that we really want to emphasize is that when we talk about versatile, we don't mean general purpose.
Right.
We don't mean that this is a general purpose tool. It's a tool that's going to be able to be used in a lot of applications, a lot of cuts, a lot of material, different types of materials. but by no means is it a general purpose tool. This is a absolute high performance tool designed to do a lot of things really, really well. But what we mean by versatile and what we want to emphasize today is all the different things you can do. So you saw some trochoidal milling there. Now we're going to go back to a little bit of heavy roughing going around, but almost, you know, contouring, peel milling type stuff. And, you know, that's of course where it really does shine, right?
Yeah. Normally when I think about versatility, you know, or not versatility, but high performance, I usually think about a tool that's specifically designed for a specific application. Like we have high performance tools that are more for high temp alloys, or maybe for hardened steels, or maybe it's for you know, a high performance tool for light finishing. But you wouldn't take that same tool and do heavy roughing. You wouldn't run it in a different material. This is a high performance tool that is also versatile, which is unique in the market, I think.
Sure. You know, if you want, you know, if you're doing milling and you want one tool in your tool changer all the time, this one is going to be at the top of the list. There's going to be so many things that you can do with it. So doing some helical interpolation here, going right into plunging.
Yeah, this is amazing. To take a tool and plunge it just like a drill is pretty amazing.
And really, that's where the geometry, you know, starts to shine with some of the things that are different between the heavy slotting, between the plunging. We've definitely seen, you know, areas where we're taking on drilling tools with it. You know, it gives you options again, right? It gives you options, and certainly the end work and special geometry that we'll talk about will do that. So now we're getting into ramping. Already ramping there at 10 degrees, which is already quite heavy.
Yep.
But we'll kick it up here pretty significantly in just a minute. So now going up to 30 degrees, and really in terms of especially ramping in steel, we'll go up to 45 degrees with this tool. So now you see a 45-degree cut. Really just amazing up and down. Got some really cool videos out there that you can check on our YouTube channel.
Yeah.
So that video, like Danny said, you know, that's kind of a way for us to break the ice, show you some different cuts if you're not familiar with the tool. And then we can move into some different points that we want to talk about. So.
Yeah, and I think we need to mention too in that video that was 4140 steel is what we're machining, in case anybody was wondering. And you know, as we kind of mentioned earlier, that this tool is general or versatile in the materials that we machine. Pretty much anything other than non-ferrous materials is what we can run. And there is a video on our YouTube channel that shows this cutter actually cutting through multiple materials simultaneously, which I don't think that would be an application that you'd actually see, but it's still interesting and cool to see that it's able to do that with no issues.
Yep. So, you know, we'll let you check it out on your own for time, basically. But yeah, it's a stack of steel, stainless steel, titanium, and aluminum all together in a stack. And again, it's just to prove the versatility. So would it be our top tool for aluminum? No, we've talked about Core 5 and some other things like that. But we get into the rest of the materials. Really, I think that's one of the neatest things about the design of this tool is that, you know, so often we are targeting certain geometry for certain materials.
Yeah. And
here it's kind of neat. We did so much design work to try to think of different features that were really required for different materials, but then how to put them together in a way that complemented each other. You know, I think one of the things, if somebody comes and tells me that something is, you know, it's really versatile, you can use it in a lot of places, my first thought's always, well, what do I have to give up? Right? And, you know, in this case, it's not about giving up something. It's really about, you know, gaining advantages in a lot of different materials, but by putting a lot of those different geometries together.
Yeah, and we can talk a little bit more about those geometries too, so everyone will understand what we're mentioning here. But I think about like our HARVI I and even our HARVI II. In order for us to run multiple materials, we had to change the geometry.
Yes, absolutely.
And until we came out with this geometry, that's pretty much been the case. You know, if we're talking about machining steels or high temp alloys, we had to use two different geometries.
Right.
And sometimes a different grade as well. But for this tool, you know, we're able to combine it all into one and be able to be high performance in all these materials that we stated.
Right.
So I guess we'll talk a little bit more about the geometries as we get into this, but I guess we want to talk a little bit more about the ramping capability, you think?
Yeah, let's talk about the ramping capability a little bit. So,
all right. So let me just show you a block. I think we have it here. So we pull up with all the. This is the test that we did when we were developing this tool, wasn't it, Steve? Where we were ramping in, and we did this 1,000 times with one tool, right?
Absolutely, absolutely. So this is a 45-degree ramp, so 45-degree, then move over a diameter, come back out. So we did this in steel, we did this in stainless steel, we did this in tie, we did it in different materials, and yeah. So the idea was, you know, we've to have the increased ramping capability. It was not to be a gimmick. It wasn't to just say that, you know, okay, in theory it can do it, or we can do it a little bit. It was to really provide that capability and make sure that it was really robust.
Right.
So definitely a lot of testing was done to be able to prove that.
So if you look at this block, you can actually see. I've activated my mouse so you guys can see that are viewing this. You can see where we ramped in at 45-degree angle, and then we traversed over to make the slot or to finish the pocket at full depth. But 1,000 of these is just really remarkable. I can't get over that steel that we've done 1,000 of those with one cutter, and the cutter still, you know, performed well.
Right. And so I think, you know, it speaks a lot, you know, to the geometry, you know, that we have of the tool, and you know, that's something that we'll definitely talk about here and highlight a little bit. Do you want to show maybe the other video with plunging and ramping here?
Yeah, I got it right here.
Okay.
Just pulled it up. So again, plunging. This is 4140 is again.
It is, yeah.
I thought so.
See some nice red hot chips come flying out of there. So doing a few straight plunges. Yep. So here now we're getting into ramping, and of course, so the cut that was just made there is not so difficult, right? Because we're more working on the outer OD.
Yeah, that's why I always want to program it.
Exactly, exactly. But now flipping it and going down certainly starts to get more challenging.
Yeah, I think about parts like aerospace parts where, especially in aluminum, you know, I think about it, but this is not for aluminum, but I'm just trying to think about the part. But when those pockets, those ribs or those ridges have a ramp on each end, you know, I always make sure we program it ramping up. But with this, you could actually program a ramp up on one side and down on the other.
Yeah, you definitely could. So there we went from a 20-degree ramp up to a 45-degree ramp. So let's maybe go in and talk about that geometry a little bit. So what we're going to do is we've got a sort of a new feature we're going to try today with our detail cam. So we've got a second camera that we're going to use in just a second to show you some features about the tool. Let's start with this a little bit, this slide, and then we'll turn that on. So, you know, a lot of people ask us, you know, what does HARVI TE stand for? And really it comes from what we call the twisted end face. So this is one of the patents that covers this tool, and one of the things that's really revolutionary, and really helps us with a smoother progressive cut, and a lot less problems, especially in the center of the tool. So able to spread that load out more evenly, and helps a lot. So let's do this. So I'm going to turn on the second camera. There's probably a delay of 2-3 seconds when I switch cameras. So if things go out for a second, come back, you know, we will be right back. So, all right, switch here. Okay, so our second camera here. So we've got, like we did the last time, we have some 3D printed models, and we're going to use those to show in a little bit better detail and talk through some things that are going on. So I've got my little Kennametal screwdriver here. So twisted end face. So you can see here, this is, you know, exactly scaled up. So this is a real tool that's been scaled up and printed. So you can see just how curved that end face is. So the curve really kind of happens in two ways, though. And this has a lot to do with this ramping capability and plunging capability. It's really, really a neat design. So not only do we have, let's say, the twist that you see there on the end when you look that way, but one of the other things that's really interesting is that we actually have a curve across these edges as well. So normally on an end mill, you know, we have a dish angle, right? And that dish angle is normally what we say is the limiting factor for ramping, right? But you know, in this case, we actually have a variable dish. So we have a curve going across this way, and that really helps protect the center of the tool. So the ramp angle significantly increases as we get in toward the center. Then the geometry that's here in the center is really designed to make sure that it's cutting efficiently to the center. And then we have nice deep gashes that also have some curve and twist to them in a couple different ways that pull those chips down into the flutes and help really evacuate them. And so that's one of the first really keys to this tool, is how this end work works together to be able to you know, achieve this plunging and achieve this high ramping.
So the twisted end actually distributes the forces differently. It's not all in one direction. So that
it does.
It spreads out those forces, and then the dish, the rolled dish on the end, so it's not straight 2 degree or 3 degree. It's actually curved, and enables it to actually not have the center work as hard. I know whenever we have a standard geometry, I've seen the center bust out, and that basically protects that center part.
That's right. I'm going to switch cameras back, so just a second. All right. So yeah, and that's absolutely right, Danny. So, you know, it's all about protecting the center, and not just protecting the center, but now, you know, typically we're cutting with the end mill, you know, from, let's say, in the OD direction, right? So that dish, all those relief angles really help us. But now, of course, to ramp like that, we're overcoming the dish, we're forcing the material in on the opposite side, and that's when things, you know, really start to get crazy. But that's where this geometry really comes in and helps out. So,
you know, we know it can ramp well. We know it can do straight ZX plunging, which we saw in the video, which is extremely impressive. But you know, I think the fact that it can do, you know, really deep slotting up to 2 times D is also impressive too. So maybe we can talk a little bit about the 2 times D slotting.
Definitely.
I know that we have a video, I think, of that as well that I can pull up. I know we've seen it already some, but this is a little bit more detailed. Let me close this, and I'll pull up the 2 times D slot.
All right. So we'll do the same thing. We'll show the video, and then we'll talk a little bit about the geometry again. So here we've already done a half D, 1D, 1.5 D, and here's the 2D slot. And you know, and as most of us know, that's something that really is quite special to be able to do that, and not just do it once, but do it over and over. So what are some things, Danny, that you think of when you think about how to tackle that? What does the end mill have to be able to do?
It has to be able to eject the chip, obviously. I mean, that's the biggest problem we have when you start running any type of tool in a very deep slot, is because it's a slot, you got a wall on both sides, you're engaged 180 degrees in that slot, and you only have 180 degrees on the opposite side to be able to eject it. So we have to figure out a way to eject the chips out. And I think that's where the geometry in this tool is, you know, really unique. And I know you might want to speak a little bit maybe about the flute shape and how we have the W flute shape. And explain how that helps us to eject the chip.
Yeah, so let's definitely talk about that a little bit, and absolutely. So it's kind of a combination of exactly like Danny said. The first thing is chip ejection, right? We've got to be able to get that chip, and we've got to deal with the forces, and we'll talk some more about the forces and temperatures as we go on, because those are certainly big factors, right? But along with that is the rigidity, and that's one of the biggest things, is trying to find a balance between having the tool able to be rigid enough to take those heavy forces, but still have the room for chip ejection. So that's where our parabolic core comes in. So that's one patented part of the design. That's also where we get into what we call the W flute shape that we'll show you in just a second. Also, what we call the chip gashes. We'll talk about that, and things like the variable helix angle, variable spacing. that's going to help a little bit more in terms of things like chatter and other interruptions. So same thing, give me just a second. I'm going to switch cameras here and
while
do
you're
a little bit
cameras,
close-up view.
While you're switching cameras, they're going to talk a little bit about the geometry. And one thing I think about in geometry is usually when I'm changing something in geometry, I'm to gain an ability, I'm taking away somewhere else. It's always give and take. And I think it's really unique with this tool, with the W flute shape that we have, that's patented, by the way, is enabling us to have plenty of chip room, but still have the rigidity that we need.
Mm-hmm.
And I think that's pretty unique, because usually what happens is if I start making those flutes deeper, I start losing that rigidity.
So switching back over here to the detail camera. So I'm going to show a little bit bigger tool here. Let me see if I can stay off the Lexan. And what we've got here, I just kind of want to emphasize this area in the center is what we call the core. So when we talk about core of the tool, that's exactly what we mean. So for rigidity, we want to make that as big as possible, right? But then we have the problem fighting against that is where the chip's going to go.
Right.
So that's where the combination of the parabolic core and this W flute comes in. So the parabolic core means the core is increasing as it goes toward the back of the tool, so it gets stronger. But then along with that, so we have this special flute shape, which is actually broken into sections, and you can kind of see this pattern here. Looks a little bit like a W. All right, so it's done in a couple different sections, and what that does is that gives us more overall room in this flute to be able to hold the chips, move the chips, and eject the chips.
Yep.
So that's really critical. Also, along with that, with those aspects are what we call the chip gashes that are here in the flute. And we'll talk a little bit more about those later in terms of how they work, but definitely they're very, very critical, to the design. Last thing that I just kind of want to quickly mention is how the variable helix and the variable index or variable spacing of the flutes kind of works together. So I'll just make a quick little demonstration. So here's another 3D printed model. All right, and this one actually is split in half. So I've got it kind of marked how that it goes together here. So if I look at it right now, all these flutes are perfectly aligned, right? So passing after another. If I take this thing and let's say I just rotate it a little bit, and now I try to match the flutes up, you can see just how much it's changed rotation.
How much asymmetrical it is.
Exactly. And that happened very quickly. Again, this is totally to scale, so we're not even talking a diameter,
right?
That we've moved down where we start to see that much. And that's designed to be at different levels down in different sections of the tool.
So the indexing is asymmetrical, but we also have variable helix as well. So
correct.
It's continually changing throughout the Z depth on the tool.
That's correct. And then of course the flutes are designed to be able to handle all that. So we've got to keep the flute width the same, how the core works, and all that. So it's kind of a balance of blending it together. So let me switch back, and we will talk about. We'll go into the next section here. Give me just a second.
The chip gashing on the flutes, and I think that's really critical for managing the heat.
Yes.
In there, so it may be good for us to talk a little bit about that as far as how we're managing the heat with this tool, which allows us to be able to run this tool either faster or improve your tool life. So we all know that heat is probably the #1 enemy of any kind of cutting action, especially with milling. But so if we can control the heat, we can do that with coolant, we can do that with other different ways, but with the geometry, with these chip gashes that we have on the flute, it actually enables us to manage the heat as well. So maybe we can talk a little bit about that too as well.
Yeah, let's do that.
And I think I've got the FEA.
Yeah, why don't you pull up? So as part of the design of this tool, obviously we made lots of prototypes. We had lots of different things that were physically tested. But along with that, we're going to take advantage of all of our capabilities, and that means force measurement. That also means things like FEA. We've got some stuff that will come out in some future white papers and conference proceedings. It'll be pretty cool. But yeah, so here's a simulation in third wave advantage showing basically how the chip gashes work. So if you want to play that through real quick, Danny, it's a very quick simulation. So if you're familiar with these, you know it takes quite a bit of time to generate one of these. But we are able to. What do we use it for? You know, do we use it to really design the tool? No, not necessarily.
But it's just another tool.
It's another tool. It's a tool that gives us a way to get some insight as to what's going on. You know, more, let's say, at the chip level. So we can look at the chips afterwards, but we can really dig into this to see. And there's a picture, Danny, I highlighted, if you want to pull that up for me, that shows a little bit about how these things, you know, really do work. So great picture. I'm going to turn on.
So this is like a snapshot of what we just saw, just a blown up snapshot of the chips being formed. We took the material out of it, so we just see the tool and the chip, right?
Correct. So I've turned on my cursor here. So here we've got what we call the rail. So basically on either side here are the chip gashes. And of course everybody sort of is going to focus on the chip gashes because that's kind of what's unique, right? You don't see that. But the big purpose of it is that we're able to create these rails. And what that means is you can see the chip is now riding on those as it's formed. And that means that we've removed the friction from a lot of surface area. And so what does that mean, right? So that means temperature goes down. It also means forces go down. And we've been able to measure that theoretically, that will show, but also, you know, very easy to measure through power monitoring and dynamometers as well. And certainly that has a big impact on things like slotting and deep cuts.
Yeah,
you know, if we can drop the overall force on the tool, less likelihood of it breaking. We can push it a little harder.
I always kind of think of the chip gashes in the flutes as being like scrapings on the rails on the machine.
Yes.
You know, the scraping on the rails on the rails on the machine, they eliminate some of the drags and the friction, but they also allow for coolant and lubrication to get between the rails so they slide better. And it's the same thing here. You know, these pockets, you know, in between these rails allow for less friction, like you said, but it also allows for coolant to be able to get in there and work its way up to the cutting edge to help minimize that heat. And we see that in the FEA analysis, and we see it in our actual chips. And I think I've got a photo here of the chips as well.
Okay.
Just showing the difference between our HARVI I, our original design, and our new HARVI I TE. So let me pull that up. Just a second here.
And of course, what Danny's going to show is not just, let's say, unique to HARVI I TE versus the original HARVI I. It really is to, let's say, normal standard flute design versus this design. So you can definitely see right away this was exactly the same cut, same cutter diameter, same speeds, feeds. Only difference really is there in the design, in the flute design, and you can see right away in the temperature of the chips. And we've got thermal cameras and other things to go into, but you know, but this is an old easy test, right?
Yeah. If you didn't have FEA, this would be the way you do it.
Yeah. And certainly that's worked for us in the past. Right? So,
absolutely.
So maybe let's show a little bit. Why don't you pull up the plots for me real quick?
Yeah, I think that'd be good to show that as well.
So we're running close on time. We want to make sure that we get to some questions. And so we've got some other, let's say, real data, but we'll show this real quick because this is also from the FEA. So real quick, what we're looking at here is we're looking at plots of the torque, the power, and the force needed to make a single chip. With the same tool design, basically the green line that you see, the green trace, is where we have the chip gashes. The red is exactly the same design, same flute, but without the chip gashes. Okay, and so what you see is initially, of course, when the tool is entering the material, cuts exactly the same.
Yeah.
Right. So forces are exactly the same. As you get further engaged and friction would start to come into play, you see the difference. You see that difference develop, and then, of course, as the chip separates, then it quickly changes. But you know, if you sort of integrate the difference between those curves, that's really what you pick up, and it depends on the material, but that can be, you know, 12 to 20% difference in forces, which is pretty amazing, and also that's helping with tool life and things like that too. So I think what I'd like to show next, Danny, is let's talk about the relief geometry and kind of how the edge of this
Yeah, because that plays a big part in the stability as well. So yeah, I can pull that up.
Okay.
Close this.
We'll take a quick look, and then we'll do the same thing with turning on the detail cam, and give us some feedback, through this. If you like this, if you like the use of the models and the details, please let us know. So, all right.
I'm going to zoom in just a little bit so you can see the.
Yeah, I think that's a great idea.
The faceted eccentric relief is what we're calling this. So this
Yes.
is a fully eccentric relief.
Correct.
But it's also faceted, which is kind of an oxymoron to be talking faceted and eccentric, but it is fully eccentric, but it still has the facets there to stabilize it. It kind of gives that ridges in there for stability.
Yes. Yep. So I'm going to switch cameras again. Let's go to a little bit bigger model. All right, hopefully we're back. So we're going to take this larger 3D print right here and move in kind of where you can see it along the edge. All right. Now, one of the things that I really want to emphasize, both with the chip gashes in the flute and with the faceted eccentric relief here, is that these tools all have a smooth continuous edge. There is always a smooth section on either side of the cutting edge. And we want to make sure that you can fine finish with these tools. You don't have to worry about any of this, showing up in your part. Okay?
Right.
It's there to help. It's not there to hurt. So what we have is, what's kind of cool about this is, if you're familiar with the term, process damping, right? So what are we really doing? With this design, we're able to provide relief. So these sections are quite heavily relieved when we get in here. But now we have these peaks, which are almost like rails now on the backside.
Right.
So we use this design on the larger diameters. So, that's important to point out. I'm just going to switch cameras back here real quick. Okay, so I just want to talk about that a little bit, is that one of the things about the design of this tool to be able to help in different materials is to incorporate some of these features. But we're also really careful to think about what makes sense for what diameter. So I saw a question earlier. We definitely want to get to some questions about the smaller diameter tools. Certainly, they have great slotting capability as well. You may see features change in different size ranges. But again, it's studied and calculated out as to what makes sense. So for instance, on the smallest sizes, you would still have the W flute. You still have the variable helix. You may not have the chip gashes. But when you get to the smaller sizes, we've tested it, chip ejection, chip evacuation is still good. We're not at a point where you're overloading the machine or overloading the tool. Same with the relief angles here. So one of the biggest things that this faceted eccentric relief does is that it lets us use the same tool geometry in steel and that same geometry in titanium and Inconel. And if we think about machining all those different things, especially titanium, we think of elasticity and spring back. We need a very sharp tool. We need a lot of relief versus steel, heavy cuts in steel. We'd like a lot more damping. And that's what's so cool about these geometries is that we're able to put some element of damping still with a lot of relief.
Right.
And that lets us flip really easily back between different materials. So, so that's, those are some key points and definitely, as we go from material to material, there's different parts that shine. So certainly the, let's say the decreased cutting forces and the very sharp edges are great for titanium. The overall strength of the tool and let's say reduced temperatures in cutting are great for Inconel. The overall vibration reduction, damping properties are great for steel. And certainly you can kind of then follow that around. Yeah, so
maybe now we can get into a few questions.
Yeah, let's take a few questions.
We're running a little bit over 30 minutes here, but maybe we can get a few questions in. So I think if I click on these and it'll publish them, correct?
Yeah, let's
see
take
here.
one here. So, see some very nice comments from some of you. Yeah, we really appreciate your feedback again. And for those of you listening on the Facebook feed, again, feel free to leave comments there. We've got people checking for them. Danny and I also will go in and look at those.
Yeah, whatever we don't get to answer today, we can, or during the webinar, we can try to respond to those later.
And there was a question about recording this presentation. You can, if you go to the Kennametal Facebook page, you should be able to watch it again afterwards there.
Right, that's correct.
I see one question, maybe we'll just jump in like this. So we talked about the smaller diameters, but should no coolant be used is a question I see.
Yeah, there. I saw that too.
Yep.
So for steels, I like to run without coolant. Now, sometimes you have to run coolant to manage the chip. Just like we talked about earlier.
Yes.
Whenever you're cutting deep cuts, you have to be able to manage that chip. You don't want to recut it. So typically, what I do in steels is try to run it without coolant. Now, if I'm running in titanium, obviously I'm running with coolant. Same with Inconel or high temp alloys. But for the steels, 4140, 1018, all that material, I would run without any coolant, if at all possible.
Mm-hmm.
But if you see that you're having problems with the chips, like say if you're in a pocket and the chips are not able to lift up out of the pocket and start gathering up, then you may have to run coolant, or an air blast would be even better to blast it out. I know that I was working with a customer this week, and we were talking about tooling up his machine with a programmable air blast, so that we could actually just put in an M code, blast the air during the program, and push them away from the cutting area and then to keep on machining. So that would be something to do as well.
I've even done that in our labs,
yeah.
For cutting tests. It's very simple to do. You have to just find your M code for it, right? You can run a nozzle there, and that's very helpful. You can do it very, just a very short burst. But again, like Danny said, just avoid recutting chips. So think about it from that standpoint. Our preference, though, in cutting steel would be dry. Now, of course, if we switch to, let's say, titanium, then our preference is
and the reason for that is to eliminate thermal cracking. So
yes.
You think about when you're running the steel and you're generating heat on the cutting edge, and then you come out. It's not like turning where you're engaged with the material all the time. This is a rotating tool, so when it's coming out of the material, it gets splashed with that coolant. You get that thermal cracking on the cutting edge. It's not something you would see with the naked eye.
Yeah.
When we look at it here under a microscope, we can see the cracking on the cutting edge, thermal cracking, and that just makes the tool life not as long as it would be.
Sure.
The other thing is running it dry actually makes the coating that we put on these cutters actually perform even better. It actually activates that coating.
Yeah.
So it's better if we run it dry in those type of applications. All right. So there's a question here about does this tool receive a coating? I think it's asking if this tool is coated. It is coated.
Yes.
We have our KCS M15 and KCP M15 grade coating on there, which is aluminum titanium coating that we have this internal.
Yep, it's proprietary grade. It's done in-house. Yeah.
Let's see what else we got here. Apologize, it takes a little while for us to go through here and find it. It looks like it's asking for a 20 millimeter diameter. I think is what it's asking for.
Okay.
We should have it in a 20 millimeter, I think. I'd have to check. NOVO, and that brings up another point. If you guys don't have NOVO downloaded, it may be a good idea for you to download it. It's free on our website.
Yes. Yeah.
It's an easy way to go in and look for all of our tooling that's available. You can check inventory. You can actually download models of not only the tools but of the holders as well, and import that right into your CAM software and doing your simulations.
Mm-hmm. Yep.
Also speeds and feeds on there too.
Yeah, exactly. You can get speeds and feeds, and it's so helpful. You can even it's so quick to be able to grab a tool holder, call it, all that type of stuff that you need to set up your job. I see a question about machining ADI. Certainly, cast irons, ductile irons are definitely all targets for this tool. Questions about tool life. Of course, it's going to vary depending on your situation, right? So There's certain targets that we would have in our minds if we were working, with a specific customer for how to set that up. Maybe just kind of one comment about tool life again, and so we talked about how we lower the forces with this tool. We talked about how we lower the temperature, and I think it's an important point to then think about what you do with it, because you could take those advantages of this tool and use it against a similar tool to extend the tool life. You could also then use those advantages to increase performance. You can increase MRR, you can increase speed, but definitely the fastest ways that you're going to get advantages with this tool, you can bump the chip load, you can bump the speed, but the biggest one is depths of cut. So both radial and axial. That is the biggest thing that you want to do. And so look at your situation. Obviously, if you're just after tool life, take that and run with it. But if you're looking at cost per part, most likely that's what you're going to start to look at is now, how can I increase my depths of cut to really take advantage of this tool? And one other point is, not only is this a tool, let's say, and it's a kind of a combination tool two ways. One is because it can be applied so many different ways, and you can take it all the way from roughing to finishing. But you can also use it in combination with other tools, and we'll make sure we always point that out. So if you're just looking for one tool to do the job, it'll take care of it. But also think about those situations where you can use it. I call it the entry ticket, to get in, make a pocket, make a slot, make an entryway into a part, and then maybe you come back with a HARVI II, HARVI III.
And do some dynamic milling.
Exactly, do some dynamic milling. One of the Trochoidal series of tools that are also very, very good for peel milling. Will this tool do all of it? Yes, but you can also think, about how to put it together. Even making an entry for an indexable, right? So you could go in as fast as you can plunge, as fast as you can ramp. You could quickly make an entry hole for an indexable as well.
Right. There's a couple more questions here, and then I think we're going to kind of wrap this up. But one question here is asking if we had compared the HARVI I TE with any of our main competitors, and we did do a lot of testing in the lab. We can't really elaborate that much about it, but we did pretty well against our competitors, I would say.
Mm-hmm.
I can't get into specifics, but for sure we want to see how we stand with our competition, and that has been done. And then there's another question here that's asking about what are the cutting parameters, or which would be cutting parameters for machining titanium, and that's kind of a loaded question. And the reason why I say that is it all depends. It depends on the diameter of the cutter, depends on what type of cut you're taking. For SFM, if I'm doing a full slot, I'm going to be anywhere from I'm going to be around 150 SFM in tie, and then when I get reduce that radial depth of cut, say like for profiling or dynamic milling, if I get down to say 10% engagement, I'm going to be around 260, 280 SFM. If I get down to 5% engagement, I'm going to be up to about 400. So when I have run as hot as 500 SFM with these tools, and with no issue at all. And again, the geometry that we have on these tools helps with controlling the heat, which allows us to go a lot faster. And as far as the chip load goes, again, that's going to depend on the diameter.
Right.
It's also going to depend on that radial engagement, because we have radial chip thinning. Once we get below 50% engagement, we have to take that into account as well. So we have charts that we know that would be the correct theoretical chip thickness, and then we use that for calculating what it would be with any given radial depth.
Yeah. So I saw two questions I thought maybe we could kind of end with.
Okay.
So first one is somebody was asking, can we explain again exactly how the faceted eccentric relief is an advantage 16 millimeters up? And I see some others asking about the different breakdowns with the geometry in different sizes. So I want to kind of address that. One of the biggest reasons that we change some of these features depending on size is, again, let's think about, obviously we have big machining centers, small machining centers, and different spindle connections. But there's always, let's say, almost a base minimum. We're not getting smaller than an HSK 40 or right. BBT 30 or something like that. Normally we're talking 40 taper up, HSK 63, stuff like that. So in that case, as we get to the smaller tools, we're not running so much into the limit of the machine and the tooling. But as we start to creep up, even, let's say, even as you go to better spindle connections, stronger machines, we're going to have more of the chance that the deflection of the tool comes into play, that the vibration of the tool comes into play, that a lot of different things happen. And so that's where some of these features come in. So the faceted eccentric, again, the biggest function that it adds is in the bigger sizes. It adds some extra damping. So without that feature, if you're running especially in higher alloyed steels, you're very likely to hear squealing, things like that, and see signs of chatter in terms of microchipping accumulating very quickly. So, basically what this does is it works with the variable helix, the variable index to kind of work together and really just simply add some extra damping on the back side. Now, when we get to the smaller sizes, we're not running at that limit. So it will change. So it'll drop down to a double eccentric relief. It still is set so that it cuts both steel and tie
protects the cutting edge.
Still protects the cutting edge. And so that will kind of change down. But even as we go down in the smaller sizes, we still have the variable index, we still have the variable helix, and we still have the W flute, and we still have a parabolic core. So,
and some of these features, it's just physically impossible to do it in those smaller diameters. And that's the reason why we had to get rid of it. I mean, you think about how these are ground, which is a very sophisticated grinding move on our grinders here. So, when we get down to those 1/8" diameters or even 3/16 or so, it's just physically impossible to get in there and grab those geometries.
Yep. So, and the last one I think I'd like to talk about is trochoidal versus pure slotting, because I think this is a interesting topic, right? A lot of people that we talk to, I know this is really common, that we get this question of, hey, I see trochoidal, it's cool, I understand it's maybe better for tool life, things like that, but then I find out that maybe it's not faster. A lot of times it's not faster than slotting, right? But most of the time with trochoidal milling, because of lower radial engagement, you're going to have lower forces on the tool, and in general, you're going to be able to attack it with a smaller machine and have better tool life. But when you've got the machine to go at it, that's where slotting definitely starts to come and take back over. So certainly this tool can run trochoidal, no problem. But the big advantage, if we could, let's say, compare, if we wanted to make the same slot, let's say we're making a slot in titanium, 6AL4V, 1.5 times deep, and we had this tool and we had a HARVI III, we would only attack it with a HARVI III and trochoidal.
Right.
Our first choice with this would be to slot.
Yeah, and it would be faster.
Yeah.
Where you're going to get an advantage with your trochoidal milling versus slotting is when you start getting above that 2 times D.
Exactly.
You start getting longer.
You start wanting to do 3 or more, especially.
Right.
Then we can pull it off in trochoidal. So
yeah, we have a great customer of ours out on the West Coast in aerospace that we're actually machining some parts. We're going 4 times D with the HARVI III in Inconel, heat treated. So this is an amazing process if it's applied correctly.
Yeah.
You definitely wouldn't try to do that with full slotting. So you have to use your own judgment and use some common sense and try to figure out which is best, whether full slotting or trochoidal milling.
Absolutely.
And if you have the part that allows it, where you can go deeper, then by all means go trochoidal milling.
All right. Well, Danny, I really enjoyed it. So we hope all of you out there enjoyed it, and please give us some comments, give us some feedback. Again, we've had so many comments and questions come in that we just don't have a chance to get to all of them. They're being recorded. We'll try to track that back up, but also feel free to ask on Facebook, and we will get back to as many of them as we possibly can. So thank you, everybody. Please stay safe and have a good day. Bye.